Welcome to our video on boundary layer separation. This is our experiment setup. We've got lights and a smoke machine to create contrast so that we can capture the flow of air as it goes over the airfoil. There's the smoke moving across the screen, showing you how it works. This is the wind tunnel that we used. As you can see, it's very close to the picture in the experimental setup. If you don't have a fancy wind tunnel at home, you can recreate this at home using a wooden spoon and heavy cardstock to create an airfoil. And then all you got to do is just blow some smoke or fog over it. The boundary layer is a region of air in which the advective and the viscous effects of the fluid accelerates from the no-slip condition along the surface to the bulk flow velocity. And this boundary layer can separate when there's an adverse pressure gradient pushing along the direction of the flow. In our diagram, you can see that the separation point is when the pressure gradient is equal to 0. So it goes from a positive in the first half of the diagram to negative in the second half of the diagram where the boundary layer is actively separating. Now, an airfoil can sometimes be modeled as a flat plate, and there's a problem in the book with a flat plate with an adverse pressure gradient, and you can find that the streamlines are dependent on both the pressure gradient, dp/dx, and this beta s term. The beta s term being the angle in which, the streamlines are based off of, based on the separation point. If you look, this is from our experiment, you can kind of see the streamline and almost that beta s coming off of the airfoil. So laminar flows are more resistant to separation the higher the Reynolds number of the laminar flow. Now, this isn't true for turbulent cases, but it is true for laminar cases, and we can kind of see that with the picture that's pulled up currently. In this picture, we can see that the angle of attack is so extreme that the boundary layer doesn't separate it at all. However, we do get to see the transition from laminar to turbulent. So here's a video of the previous picture that you just saw, and so we'll let it play for a second and you can watch it. So here's one more picture for you. It's at a higher Reynolds number and a lower angle of attack, and you can see that it's still kind of based off that beta s. Now, if you look very closely at this picture, you can see a Davis-Harris shaped vortical structure. I'll zoom in a little bit. Now, maybe I'll zoom in a little bit more.